I want to do this together is to make sure I don't miss any dates that are coming up that we need to adjust. So first page is outcomes. Yep, we got to do Moodle. Student responsibilities. Text, same book. I reached out to the publisher to see if I could get you guys an ebook, and they never replied to my email. Was it? Wow. You should take them with you when you evacuate. Good. Make sure they, like, I've rented this book. Okay, so here's our first dates. Midterm exam. We're going to change that to whatever a week after October 11th is. Is it the 18th? Okay. So the first 6 section exercises, October 18th. I'm not changing the course paper. I got to grade them. I need that time to grade them. Okay, important dates. Here's another thing. Last data drop. As far as I have heard, they are not changing this. Okay, it's going to be Thursday, October 25th. You will have your grades before Thursday, October 25th. You will know where you stand in the class, and if you have your midterms back before then, I think we'll have a week for you to come talk to me if you're starting to freak out. And I'll try to walk you down a little bit and say, okay, let's think about this. The course paper due, that's going to stay the same. Here's something I learned today. Here's something we need to fix about Moodle. I am guilty of this. Apparently, it's really bad for all of your instructors to make things due at 11:59, because you know what happens? All of you log into Moodle at 11:55. And so the problem that we have with Moodle and the slowness of it is the fact that too many people are trying to use it at the same time. So I'm going to change this to 10:59. Okay. So that way, it's going to cost you an hour, but you'll actually be able to log into Moodle. Does that make sense? Yeah. We had this discussion at Faculty Senate yesterday, and somebody complained, Moodle doesn't have enough bandwidth. Well, that's not how Moodle works, first of all. And so somebody intelligent said, actually what the problem is we cannot afford a server that allows 10,000 plus people on it at the same time. And then somebody from the Moodle people raised their hand and said, yeah, on this date we had 1,200 people try to access it all around 11:59. And it's because instructors, so personally for me, in the future, I will not be using late in the evening as a time because other instructors don't quite understand that. So just to, to learn something today. So that's changed to 11:59. Final exam, we're still good for December 30th, or 13th, sorry. The times hasn't changed. Nothing has changed with final exams. All right. We missed the following days. The 13th was online. That lecture has already been posted. The 20th we did online. And the 27th I did online. Okay. So now, here's what we'll have. We'll have the midterm exam move from the 11th to the 18th. I will grade them really super fast and post the grades on Moodle. And then you should have about a week to decide if you want to drop the class or not. This also gives you an extra week to sort of catch up. I will not be adding more content to the midterm. The midterm will still be 1 through 6, even though I'll taught 7. We clear on that? Okay. So all the videos are online, and I can tell 2 things. 1, how many times you've watched the YouTube video, and 2, when you click on the link to go to the YouTube video, so I know whether or not you're sort of watching the videos or not. Sorry, but I do know. And I know you're not watching the video. So also the hybrid part, the one where I go through and show you how to do it by hand, you're not watching those either. So when you come to me and you say, Dr. Wood, I'm having issues with the class, one of the first things I do is I pull up your Moodle profile and I go, well, I can see every link you've ever clicked in Moodle, just so you're aware of that. And we'll have a discussion about why didn't you ever click on this link? Right? So if you've taken, for this class only, if you've taken the last 3 weeks off, you're going to have to watch some videos. And yes, my mic pops because it rubs against my shirt, and there's nothing I can do about it because none of you want me to go shirtless. So just sit down and turn the volume down a little bit lower so you don't get the scratchy mic pop. All right? And watch the videos. It's the deal when you signed up for a hybrid class that you were going to do some of the work online. It's time to actually do that now. It's October. All right? I think we're good. And that's the end of the syllabus. Any other changes, requests you would like made? What, Allie?
So we're only going to have to do 6 exercises?
Yep. Only 1 through 6. The midterm will only be on 1 through 6. The exercises will only be 1 through 6. Yep. I don't want to get too many different dates to confuse people. Okay? All right. Very briefly, to recap what you missed so that when you didn't watch the videos, you won't be completely lost today. Here's what I did over the last 3 weeks. First video, measures of central tendency. This is where I actually introduced some math and talked about things like this with a formula. X bar equals sum of x divided by n. The sigma is a summation sign. It means add up all individual values of. So if you have a data set of 5 people, x1, x2, x3, x4, x5, you add x1 plus x2 plus x3 plus x4 plus x5. Okay? That's what the summation sign says. So that way you don't have to write x1 plus x2 plus x3 plus x4 plus x5 plus x6 all the way down to the last one, which is usually x sub n. So there's a lot of notation where math people can use. They can put stuff at the top of the sigma and stuff at the bottom of the sigma and stuff under the sigma. I just want you to simply say, it's a sigma, add together, sum. This is something you've learned. Again, Abby learned this last year, 2nd grade, we learned averages. We're just going to give it a different name, call it a mean, and throw some Greek letters in there to make it university level. The takeaway from this, and talking about these different measures of central tendency, was how the differences between them can reflect the variability in our data set. So ideally, if you have a data set and the mean, the median, and the mode are all the same, that's a good sign that this data set has a normal distribution, or this bell shape. It's a good sign. But there are times when you have outliers, or you have a skewed distribution where out here in the tails, they pull the mean towards the tails. So this is Shaq's shoe size. Right? Basketball players with their gigantic feet because they're tall and they need a bigger pedestal to stand on or whatever. Biology. They pull the mean. So Shaq in his size 23 sneaker pulls the mean. There's the condition of outliers in the data. And because the mean uses all of the data, the median only uses, well, one data point in the middle. And the mode only uses the most, the distribution will have different numbers for them, mean, median, and mode. So that tells us that our distribution is not normally, well, is not in the shape of a normal distribution. Okay. If you have more than one mode, it means you're multimodal. So this is a bimodal distribution. It has two humps. So what do we know from measures of central tendency? Well, we know what's most likely to happen. We also know something about the symmetry of the distribution. So it tells us if our bell shape is lopsided or not. It doesn't tell us much about variability. So that was the next lecture. This was week 4. This was talking about the concept of why we need to understand variability. And the example that I used in the video was this idea of looking at quiz scores. And both of these sets of quiz scores have the exact same mean. You add them all up, divide them by 6, they all have the same mean. I think the mean was 5. 10, 20, 30 divided by 6. Yeah, mean was 5. But which one would you rather be in? Would you rather be in class A or class B? I'm actually curious about this. Which one would you rather be in as a student? You don't know which grade is yours, but you know you're going to get one of those grades. Allie? Allie wants to be in the class where 3 people fail and 3 people do good. Anybody want to be in A? Why? Yeah, because in A, only one person really doesn't get anything. Whereas in B, 3 people get like nothing. Right? So I can work with a 40, but I really can't work with a 1. Right? Allie's just betting on she's one of the 9s or 10s. Yeah, I got it. So this is the idea of variability. And what variability measures is how much difference exists within a data set. So if we have these 3 normal curves, each curve has a normal distribution, but we'll notice that the shape of the distribution changes. So they all are centered on the same mean. That's what the line in the middle is. They all have the mean, median, and mode. But what's different is the shape of it. And for some reason, whenever I look at curves, I can't help but use like body image terms, right? Like we all have sort of preferences for shape. There's an aesthetic to it. Like, I don't really like being with tall people because I'm short, right? Or I'm a short person. Well, the curves sort of have shapes to them themselves. So we have a tall one, we've got a short one, but as it gets shorter, there's more variability in it, and it gets wider. And so what we have is we actually have, looking over here, we have more of our data further away from the mean. And that's what the height of the curve expresses, the amount of data. And again, I use this example from a weight room. If you turn your head or your computer screen when you're looking at it, you can kind of see that there's a normal distribution in there. And in the video, I go on about this for like a good 10, 15 minutes. This is fascinating to me. There are other measures of variability, but they all stink. The range just tells you the width of your data set, from the highest score to the lowest score. There's something called the interquartile range, which, because the range itself can be manipulated by one outlier, again, Shaq's foot. The interquartile range says, instead of looking at all of these, let's just look at these. Let's just look at the ones in the middle. How wide is the middle? 50%. And then there's the one that involves the math that is by default the best one because it has all the math. And it's called variance. And what variance does is it looks at the individual distance for every observation from the mean. So if there are 5 people in your data set, you are going to have 5 steps. So for each individual observation, you're going to subtract that value from the mean. And this is why it's so important that we have computing in statistics. So that when you have a data set of 65,000 people, you don't have to do this 65,000 times. Subtraction, next column. Right? It'd be like you need a huge roll of paper to get this done. Computing is your friend. So you take the difference, and then we know that the sum of all the differences from the mean will add up to 0, because that's what the mean does, is it provides us the equal middle point of everything. So we square it to take that away. And again, all this is explained on the video. So we get something called variance, and then I tell you the variance is nice, but the standard deviation is better. And I throw a square root in there. So what you're actually doing is taking the square away from the variance by taking the square root. Pro tip, turn your phone sideways so you get more buttons on your calculator. And all of this is important for us because of something called the empirical rule. The empirical rule helps us understand where our observations are in our data set. And it turns out that the shape of the normal curve, right, that bell, let's call it bellness, that bell shape, no matter how tall or wide it is, its scores, the volume underneath the bell, are arranged in a predictable manner. So 68% of our observations 68% of our observations will be within 1 standard deviation from the mean. So if our mean is 5 and our standard deviation is 2.5, %68 of our observations will be within 1 standard deviation from the mean. Why? Magic. Okay, it's actually geometry, but that's just the way the normal curve works. So the bulk, right, a preponderance, 68% of your observations are going to be close to the mean, within 1 standard deviation on each side. 2 standard deviations give us 95% of our observations. Okay. So within 2 standard deviations from the mean, about 95% of our observations. And as we get further and further out, less of the observations. So by the time we get to 3 standard deviations away, we are pretty much all of our data should be within 3 standard deviations, right? 99.7%. And if you're more than 3 standard deviations away, then you're probably one of those like Guinness World Record holders. Like there's that guy in China that's 10 feet tall. I don't know if there is one, but there could be. There's like a few billion people there. I'm sure one of them's 10 feet tall. Right? He's way out here. Probably has a really big shoe size too. Okay. So this is called the empirical rule, and it's great for us because we just sort of know, well, yeah, we should be within this many standard deviations, particularly 2. Right. I do spend a couple minutes on the video reinforcing this fact that the bell-shaped curve comes from a formula, and that's it. And it looks awful, but it's really not. I mean, all those letters there aren't that difficult. But what I did want to show you was that the shape of the curve is a function of really 2 things that aren't constant, and that's the mean of the data set and the variation of the data set. So that's why we spend a week on mean and a week on variation. And when we look at the normal curve, we see that this thing is just a function of mean and standard deviation. So y equals 1 over the square root of 2 pi, not 2 pi, 2 pi. Pi is 3.14. So that's a constant, right? 1 over the square root of 2 times 3.14 times e. And I have to admit, I kind of blanked out in middle school math when we did the logs. Like, I never really truly understood it. I just always just hit the button and let the calculator do all the work. So don't ask me to explain logarithmic functions. I don't want to. The E button, and then you would type something in and it would give you the answer. You guys remember that from middle school, high school math? Yeah. And the number that you type into the computer is a negative x minus. X is the point along the curve where you're going to draw it. Because this is all an equation. This is why you had to actually buy the $75 to $125 calculator that I've got like 8 of in my office. Because of stuff like this. Because you're drawing a shape. So you put in some random value of x, and then the distributions, that's what mu is. Right? Mu is our population parameter for the mean. Squared divided by 2 over, or 2 times the standard deviation. So sigma, that's a baby sigma. little O with a hat on it. That's a baby sigma, or lowercase sigma, and that represents variance. You don't have to know how to do this. I'm just showing you where the shape of the curve comes from. It comes from an equation. I got a book in my office that has lots of equations like this for different shapes. There's something called a Weibull, W-E-I-B-U-L-L, a Weibull distribution. It has its own equation that creates the Weibull distribution. There's something out there called a Poisson distribution. Okay? So mathematicians sort of create these shapes. This is our standard normal distribution. Okay. The last week, that we missed, we focused in on this idea of the normal distribution. I spent a week on this because we have to become comfortable with what a normal distribution looks like. Now remember, this is a way for us to represent the full range of data that we have. So it could be shoe size, it could be years of education, it could be people's incomes. They'll all have a bell shape, but where that shape is relative to the number, right? Whether this is income or this is shoe size, okay? Number of days that you live in your life. We can do a survival model. How many days or years do people live? That's an actual thing. It's called actuarial sciences, trying to predict how long people live. Insurance companies need it to figure out how much to charge you in life insurance. Whatever our data is, it has a distribution. Different means, but same variances tells us that the curve just sort of moves along the number line. It's the different variation that gives us its different height to the curve. So we spent 2 weeks on understanding what central tendency is and variance is, so that I can spend a week on what the normal curve is, because we're actually going to use it in a few different ways. And this is the time where we take a turn in the class to actually go into the idea of probability theory. Okay? So this is our standard normal distribution, right? It has the perfect proportions of aesthetics. We like this. This is how we're going to draw them. Not too tall, not too short, not too wide, not too skinny. Our ideal. The real kicker is that because of math, we can have this x-axis be different things. So we can have it be the raw value of the data we're looking at. We could do that. All right. So this could be, let's call it shoe size. Stop it. There we go. So we could put an axis here. I can just break stuff too if that's what the computer wants. We can put an axis here that is shoe size. What's the average shoe size? Nobody knows. Just shout out a number, 8. All right, 8 will be the center of our curve. But also, 8, because it's the mean, is where our standard deviation equals 0. Right? If the center of the curve, you're not, if you're on the center of the curve, you're at the mean, how far away from you are you from the mean? 0. Because that's what standard deviation units are. How far you are away from the mean. Remember, if we go out 1 standard deviation unit each direction, how much should be in between those 2 spots on the curve? 68%. Okay, so there's 68% in the middle. So now we have another thing that we can create an axis for. How much of the percentage are we on the curve? So I think that if you take 68%, that's the space between 16% and 84%. Right? 84 minus 16 should leave you with 68. So what we've done here is we've now thought about our data in a different way. We're thinking about it in terms of volume. How much is in between? So what we do in statistics is we try to look for where we can find, I don't want to call it a coincidence, where we can find an opportunity to simplify or to use the information we have in more than one way. To sort of see opportunity. Because if we can have an opportunity, we can do more with what we already know. Bucket on the floor kind of thing. If we can notice that volume expressed as a percentage is between 0 and 1, what else can we have that's between 0 and 1? Well, we can have area. Area is between, area is, we can make this between 0 and 1, right? Like actual physical space. How much area is under a normal curve? 1. Always. It's always just 1. 1 what? Doesn't matter. It's always 1. It's not a cubic foot. It's not an acre. It's just 1. Because this isn't actually a physically real thing. It's just math. Percentages are usually expressed in a number between 0 and 1, right? From 0% to 100%. Which again, bucket on the floor, if you have 100 per 100, because that's what percent means, per 100, cent is 100, centimeter. What is 100 per 100? 1. See, by knowing math, I can make explaining something like a percentage seem stupid. Like, why do you need to know what percent actually means in Latin? Because mathematically, it tells us what it is. Anything that is a percent is always that number divided by 100 per 100%. Bucket on the floor. All right. What we're going to do, and what I wanted to talk about for all of class today, but I only have 15 minutes remaining, is another number that we use in math that is sort of based on the number 1. And that's probability. All right? What is the probability of an event happening? And so on to today's lecture. So probability is the concept where we try to quantify the chance of something happening typically the easiest way for me to explain probability is to go into gambling land, where your math skills can be used for both good and evil. Some of the most lucrative poker and blackjack players are the ones that have an innate ability to understand probability. I'm not a good poker player, but when the poker craze hit like 10 to 15 years ago, I might have participated in some poker activities. And I always had the hard time understanding why. Why does a hand that involves 3 of a kind, so 3 8s out of your 5-card poker hand, why is that a better hand than my hand of 2 pairs, which involves 4 out of the 5 cards? Like, it's harder to get those 5 cards than it should be. Like, I have more cards. I have more cards related to each other. My 2 pair of 4 cards should beat your 3 of a kind. But it's actually statistically harder to have 3 of the same card than it is to have 2 pairs, because it's really not all that hard to get a pair. It's really not all that much harder to get 2 of the pairs. So I always had that problem, and I'd always be like, I don't know if I have a good enough hand. Because I think there's like, haha, I got 4 cards that are the same. No. 3 of a kind's a much better hand. And that's why I don't play poker professionally, because I can't even remember which hand is better than the other one, much less figure out the odds of getting a good hand given the crap that I've been dealt. Because Carl's a horrible dealer. Never play when Carl's dealing. Okay. So I like to stick to roulette. Don't roll your eyes. She did. Why are you rolling your eyes? I like roulette, because you know what? Roulette is based upon probability that you can observe. 1 ball around the wheel. And huh?
I'm pretty sure those are magnetic.
They're not magnetic. They bounce. All right. 1 ball, spin it around the wheel, and it's going to fall into one of 38 slots. So I know what the outcomes will be. You have 1 through 36, alternating in red and black, and you have 2 zeros, the single 0 green and the double 0 green. Now the greens are where the house gets its advantage, because when you play red or black, you have 18 winning outcomes and 20 losing outcomes. And my ability to understand probability in math allows me to play roulette. Like, you can see that I can clearly talk about roulette. You're like, this guy knows what he's talking about. When it comes to poker, he's like, no, the hand with 4 cards should be better than the harder hand of 3 cards. You're right, he really should not play poker. So my fundamental ability to understand things like probability as it comes to the outcomes that I can easily see, the little thing, I don't know what they call the ball that goes around the wheel, or with craps, dice. We all understand that when you roll a die, it has an equal number or equal probability of landing on any number, right? You should. Those aren't magnetic either. They're just little chunks of plastic. All right. So probability is the likelihood of an occurrence given all possible outcomes. And the simplest way to teach somebody probability is by flipping a coin. Why? Why is flipping a coin an easy introduction to probability? Yeah, because there's only two options. 2 is the minimum number of options you can have. Right? If you only have one option, it's not really probability. You can flip a coin and get a head, or just making sure. Right. So if we flip a coin, you can get a head or a tails. So what is the probability of each event happening? No. Look at the screen. Yeah. We're in math now. You can't just like shout out random numbers. It's not 50. It could have been 50 what? Say another word after 50 to make it 1/2. 50 per 100%. All right. So the outcome of a head is 50%, or 1/2. Okay. Or we can also think of numbers one other way. We have fraction. We have percentage. We also have proportion. Okay. You were taught this in school, but nobody ever said, hey, we're going to talk to you about another way to understand fractions. And so I'm trying to teach Abby fractions, not using the numerator-denominator thing. I'm trying to teach her using proportions. It's not going so well. Turns out you actually need to understand the fraction part first. Okay? A number between 0 and 1 is called a proportion. It's just like a percentage, right? A lot of time we talk about things as if they're a percentage, but they're actually proportions. It's October. October means, for me, October baseball, which means I don't get to go to bed till 1 o'clock in the morning every night because the commissioner won't respond to my letter about not having games start at 8 o'clock at night. In baseball, the stats that we use for batting average is a proportion, right? A batter bats 326. That's a proportion. This is actually why I had to teach Abby about proportions, because I'm trying to teach her about batting averages, and she's like, but that doesn't make any sense. It's not a percentage. And I'm like, you're right. It's not a percentage. And so when I keep saying this batter will get a hit 3 out of 10 times, and she goes, well, no, he'll get a hit 0.3. And I'm like, but that's a proportion. It's not an average. And this is why I think about these things so that I can explain them to you all. And you're just like, yeah, this is what it is. It's a number. But there's a certain type of number that it is, and it's a proportion. So probability is the ability to understand the probability, the chance, the likelihood. That's a word we're going to need a lot in this class later on. Likelihood of an event happening, given all possible outcomes. You ever had this problem? You've gone shopping. It's time to check out. There are 5 lines in front of you. Which line is the fastest? It's always the one I don't choose, but I don't know that ahead of time. Right? Do you know anybody that has great skill in picking out the fastest checkout line? If you do, ask them, like, what's your method? Because I'm always choosing wrong. At one point, I thought it was the number of people, but then you got to look at the number of items they have and how long is that transaction going to take. I learned that by watching like too many hours of extreme couponing. It just sucks you in. All right. Here's the thing about probability. Remember, the sum of all possible outcomes has to be 1 or 100%. They have to add up to that. So if anybody ever tries to tell you that the chances of something happening is 125%, don't believe them because they don't understand probability. The numbers don't work that way. And they're probably trying to talk to you about odds ratios, but nobody uses odds ratios anymore, so they don't know what they're doing either. If we have all of the outcomes, we can add them together. This is known as the addition rule. So this is why I don't understand in poker that when I have to calculate the probability of two pairs, what I need to do is to calculate the probability of one pair plus one other pair. Here's a very quick, if I have it. I have 5 minutes left. What's the probability of when you're rolling a die, one dice, that you get an even number? No. I'm being a stickler. What is the probability of getting an even number? No. That's what I want. I want 3/6. Because the formula says the number of times you see that outcome divided by the total number of outcomes. When you roll a die, how many outcomes are there? 6. Not 2, 6. So it's 3/6. How do we know that? The probability of getting a 2 is 1/6. The probability of getting a 4 is 1/6. And the probability of getting a 6 is 1/6. That's 3/6. Okay. Why is this important to us? Okay. Well, we have a very good reason. This is going to be important to us because we're going to take that normal curve and we're going to have the area represent probability. And the thing that we're going to do is the probability of how far our score is away from the mean. And we're going to take that area, that percentage that we find, and we're going to say, well, that's the probability of something happening. We're not going to do that today. I'll finish this lecture next week. I'll condense 7 down a little bit. I want to say one more thing before you all leave. I forgot to do something. I told you in class I was going to bring this, and I didn't. But I have posted it in Moodle, and you'll need it for Section 5, particularly for the Section 5 exercises. This is a normal distribution table. This is why you have to watch the videos, is because I show you how to use this. I told you I was going to bring them to class today, but I forgot because I completely forgot until I got here. You need to print this out. And in the video, I explain why you need to use the one that I use instead of the one that your book has in it. Okay? So when you come to class next week, I will have copies of it for you. This is not something that you can have too many copies of. You have one in your book, you'll have one in your notebook. Now that you have a notebook, this is something we'll use a lot next week. So I'm sorry I forgot to do that today, but we'll do this next class. We'll finish Section 6 and on to Section 7.